Seismic attenuation, concepts, mechanisms, and applications. Introduction. Earthquakes are among the most powerful and destructive natural phenomena on Earth. Understanding how seismic waves behave as they propagate through the Earth's crust is fundamental to seismology, earthquake engineering, and hazard assessment. One of the key processes influencing seismic wave behavior is attenuation, the gradual loss of seismic energy as waves travel through different geological media. Seismic attenuation is crucial because it directly affects ground motion intensity, seismic hazard estimation, structural design, and seismic imaging of Earth's interior. By studying attenuation, scientists can better interpret seismic data, forecast potential earthquake impacts, and even map subsurface features such as reservoirs and fault zones. This video explores the concept of seismic attenuation in detail, covering its definitions, types, physical mechanisms, measurement techniques, influencing factors, applications, and future research directions. What is seismic attenuation? In simple terms, seismic attenuation refers to the reduction in amplitude and energy of seismic waves as they propagate away from the source. Unlike geometric spreading, which reduces amplitude simply because wave energy spreads over a larger area, attenuation involves actual loss of energy primarily through absorption and scattering within the Earth's materials. Mathematically, attenuation is often expressed using the quality factor, Q, which represents the efficiency of wave propagation in a medium. High Q, low attenuation, waves retain energy longer. Low Q, high attenuation, waves lose energy quickly. Thus, Q provides a quantitative measure of the medium's ability to transmit seismic energy without significant loss. Mechanisms of seismic attenuation. Attenuation results from multiple physical processes. These can broadly be categorized into intrinsic attenuation and scattering attenuation. 1. Intrinsic attenuation. This occurs when seismic wave energy is converted into heat through internal friction and an elastic deformation within rocks. Key processes include viscoelastic relaxation. Rocks are not perfectly elastic. They exhibit time-dependent behavior where strain lags behind stress. This lag dissipates energy as heat. Dislocation motion. At the microscopic level, movement of dislocations within mineral grains dissipates mechanical energy. Grain boundary friction. Relative movement between mineral grains causes frictional heating. Fluid-solid interactions. In porous rocks, fluids can move relative to the solid frame, causing energy loss, like squirt flow and Biot's global flow. Intrinsic attenuation dominates at high frequencies and in media with significant heterogeneities like sediments. 2. Scattering attenuation. Scattering occurs when seismic waves encounter heterogeneities such as fractures, faults, voids, or abrupt changes in rock properties. Instead of being absorbed, wave energy is redistributed in different directions. Coherent scattering alters the waveform but preserves energy in the forward direction. Incoherent scattering redistributes energy away from the main path, effectively reducing observable amplitudes. Scattering is particularly significant in highly fractured crust, volcanic regions, or sedimentary basins where impedance contrasts are strong. 3. Geometric spreading vs. attenuation. Although geometric spreading reduces seismic amplitudes, it is not strictly considered attenuation because no energy is lost, only distributed over larger areas. However, in practice, seismologists must carefully separate the effects of geometric spreading and attenuation when analyzing ground motion. Factors affecting seismic attenuation. Several geological and physical factors influence the degree of seismic attenuation. 1. Frequency of the seismic wave. High frequency waves attenuate more rapidly than low frequency waves. This explains why distant earthquakes are often felt as long period ground motions rather than sharp, high frequency shaking. 2. Rock properties. Crystalline rocks, like granite, basalt, typically have high Q values and low attenuation. Sedimentary rocks and unconsolidated materials exhibit low Q and strong attenuation due to higher porosity and fluid content. 3. Temperature and pressure. Higher temperatures enhance inelastic relaxation processes, increasing attenuation. In deeper lithospheric regions, temperature strongly governs Q values. 4. Fluids in pore spaces. The presence of water, oil, or gas increases attenuation due to fluid-solid interactions. Seismic attenuation is often used in hydrocarbon exploration to identify fluid-bearing zones. 5. Crustal heterogeneity. Fault zones, fractures, and volcanic conduits enhance scattering attenuation. Stable cratonic regions, being more homogeneous, transmit waves with minimal energy loss. Measurement and quantification of seismic attenuation. Seismologists use several methods to quantify attenuation. The most common approaches include 1. Spectral ratio method. Compares amplitude spectra of seismic waves at two different distances from the source. The slope of the logarithmic amplitude ratio with respect to frequency gives attenuation. 2. Coda wave analysis. Utilizes the coda waves, the tail of the seismogram, which result from multiple scattering. Since coda waves are dominated by scattered energy, analyzing their decay provides robust estimates of Q. 3. Two-station method. Similar to spectral ratio but specifically uses data from two stations aligned along the wave path to isolate attenuation effects. 4. Inversion techniques. Uses large datasets of earthquake records and applies inversion algorithms to estimate spatial distribution of Q values. 5. Laboratory measurements. Rock samples are tested under controlled pressure and temperature to measure intrinsic attenuation directly. Helps in calibrating field observations with physical models. Regional and global variations in attenuation. Attenuation varies significantly across tectonic settings. Stable continental interiors, like Canadian Shield, Indian Craton. High Q values, low attenuation. Earthquakes can be felt over very large distances. Active tectonic regions, like Himalayas, California, Japan. Low Q values due to fractured crust, high heat flow, and fluids. Seismic energy dissipates rapidly. Volcanic and geothermal areas, like Iceland, Yellowstone. Extremely high attenuation because of partial melts, fluids, and strong heterogeneities. Oceanic lithosphere. Generally higher Q than continental crust, except near mid-ocean ridges where high temperature lowers Q. Applications of seismic attenuation studies. Understanding seismic attenuation has broad applications across seismology, engineering, and resource exploration. 1. Earthquake hazard assessment. Attenuation models are key to ground motion prediction equations, GMPs, used in seismic hazard analysis. Helps determine expected shaking intensity at different distances from a fault. Critical for earthquake-resistant design of buildings and infrastructure. 2. Seismic imaging and tomography. Attenuation tomography maps Q values across regions, complementing velocity tomography. Provides insight into temperature distribution, fluid content, and heterogeneity of Earth's interior. Used to image subduction zones, magma chambers, and fault zones. 3. Hydrocarbon and mineral exploration. Attenuation anomalies can indicate fluid-saturated zones such as oil, gas, or water reservoirs. integrated with reflection seismology to reduce exploration risk. 4. Volcano monitoring. Attenuation is sensitive to magma and volatile content. Elevated attenuation beneath volcanoes often indicates magma movement, providing clues for eruption forecasting. 5. Nuclear test monitoring. Seismic attenuation is used in distinguishing natural earthquakes from underground nuclear explosions. Explosions typically generate high-frequency waves that attenuate differently compared to tectonic earthquakes. Challenges in attenuation studies. Despite advances, several challenges remain. 1. Separating effects. Difficult to isolate geometric spreading, scattering, and intrinsic attenuation in real seismic data. 2. Frequency dependence. Attenuation is highly frequency dependent, but exact scaling laws remain uncertain. 3. Regional variability. Strong variations in attenuation within short distances complicate the development of universal models. 4. Data limitations. Requires dense seismic networks and high-quality recordings, which may not be available everywhere. 5. Nonlinear effects. At very strong shaking levels, rocks may behave nonlinearly, altering attenuation properties unpredictably. Future directions and research trends. The study of seismic attenuation is evolving with new technologies and methods. 1. Dense seismic arrays. Networks like USARRAY and Japanese HiNet provide massive datasets enabling high-resolution attenuation mapping. 2. Machine learning applications. AI algorithms are being developed to automate Q estimation and pattern recognition in attenuation datasets. 3. Full waveform inversion, FWI. Advanced modeling techniques incorporating both velocity and attenuation provide more realistic Earth models. 4. Laboratory advances. High pressure, high temperature experiments are improving our understanding of attenuation under mantle conditions. 5. Multidisciplinary integration. Combining attenuation with geodesy, geochemistry, and electromagnetic methods for holistic Earth system imaging. Conclusion. Seismic attenuation is a fundamental process governing how earthquake energy propagates through the Earth. By converting wave energy into heat or redistributing it through scattering, attenuation shapes the intensity and distribution of seismic shaking that people and infrastructure experience. Understanding attenuation is not only crucial for seismologists but also for engineers, urban planners, disaster managers, and resource explorers. With ongoing advances in instrumentation, computational modeling, and data analytics, our ability to quantify and interpret seismic attenuation continues to improve, offering deeper insights into Earth's structure and better tools for mitigating earthquake risks.